Good morning, sir.
Good morning,
Good
sir.
morning, sir.
Sir,
Good morning. Without wasting any time, let us start with the discussion. Last class, if you remember, we were discussing about IUPAC nomenclature. Yes or no? Last class, if you people remember, we were actually discussing about IUPAC nomenclature of complexes. And before that IUPAC nomenclature, we have seen how to calculate the oxidation number, number of chelating ligands. Yes or no? And coordination number. And before that, we have also seen how to figure out the vibrational stretching frequencies of CO bond and MC bond, which is stronger, which is weaker. All such discussion has been done. So let us solve a few more examples of a nomenclature today and then proceed with your next concepts of effective atomic number, Werner's theory, and valence bond theories. Look at this carefully, students. NiDMG taken twice. What is the name of this complex? You have to answer. NiDMG taken twice. NiDMG taken twice. I have told you what is DMG earlier as well. And I have given the complex of DMG to you, if you remember. While you are discussing bidentate ligands. Yes or no? Let us go back to that. Yeah, here. If you remember, we have discussed a complex like they have just mentioned DMG, dimethyl glyoxymetro. It is a bidentate ligand, but I have given an example like NiDMG taken twice, where nickel is in +2 oxidation state. Why it is so? Because in 1 DMG, you are going to have only O minus. In 2 DMG, we will be having 2 O minus. Like this is CH3, C double bond and OH, carbon carbon single bond, CH3, C double bond and O minus. So if you look at one molecule of dimethyl glyoxymetro, you will be having only one oxygen with a negative charge. All other atoms are neutral. Similarly, other DMG also have only one oxygen with a negative charge. So nickel should be in the +2 charge to neutralize all that 2 minus charge. So NiDMG taken twice. What is the name now? Name. First you have to name what? First you have to name the cation or anion?
Cation.
Cation. Yes, Shefali gives bis dimethyl glyoxymetro nickel 2. Very good. Yes or no? Because if you look at this complex given to you, is it a cation or is it an anion? It is not a cation. Yeah, it is not a cation or not an anion. It is not dissociating into two ions. Rather, it is a simple neutral complex. So NiDMG taken twice. So here we have two dimethyls glyoxymetro. So in the dimethyl glyoxymetro already we have used di. So I cannot use di of dimethyl glyoxymetro again. So we have to use bis. So bis brackets dimethyl glyoxymetro. I have completed naming of the ligands. Yes or no? After naming of the ligand, what I have to do? I have to proceed with the naming of the metal ion. Since metal ion or metal is not in the anionic complex, so you can simply write nickel. Else we have to write nickelate, and oxidation state of nickel is 2. Base dimethyl glyoxymetro nickel 2. Is that clear, students?
Yes,
Yes,
sir.
sir.
Yes, sir.
Very good. Try to name this Na3AlF6. It is also called as cryolite. What is IUPAC name of this compound? Na3AlF6 is also called as cryolite. But what is the IUPAC name of this particular compound? We have to answer this. How the splitting or dissociation occurs? 3Na plus and AlF6 3 minus. Yes or no? 3Na plus and AlF6 3 minus. First you have to name the cation. Cation is Na plus, so sodium. Then you have to name the anion. Anion is AlF6 3 minus. So we have only one type of ligand. What is that? Fluorine. How many are there? 6 are there. So hexafluoro, sodium hexafluoroaluminate, not aluminium. Why? Because the complex ion is the anionic ion, and in the complex ion you have metal. So that is why aluminate. And oxidation state of aluminum is 1 aluminium. Let us say oxidation state of aluminum is X. 6 fluorines, 6 into -1, that is equals to -3. So X should be +3. So sodium hexafluoroaluminate 3. Sodium hexafluoroaluminate 3. Try to name this compound. H2PtCl6. Very good compound this one. H2PtCl6. H2PtCl6, if it dissociates, it gives what type of ions? 2H plus. Yes, very good. PtCl6 whole -2. Now give the name.
Hydrohexachloroplatinum.
Platinate.
Okay, fine. But the exact name of this compound is this one. Hexachloroplatinic 4 acid or chloroplatinic acid. Write down this. If you apply your general logics of IUPAC nomenclature for naming the complexes, you should first name the cation. So here you have hydrogen. Then you will be writing hydrogen, hexachloroplatinate, oxidation state of platinum is 4. Hydrogen hexachloroplatinate 4. That is the generally predicted name. But why this name has been given as hexachloroplatinic 4 acid or a chloroplatinic acid? Why? Because this H2PtCl6, it is an acid, it is not just a salt. Although it is a complex ion, what are complex salts? Complex salts are those salts which do not dissociate completely into ions. Yes or no? But here, if you look at this particular H2PtCl6, although it is a complex, it is not just a complex salt. It is a complex, but not a salt. It is an acid. So that is why its name has been given in the other way, hexachloroplatinic 4 acid. You have to remember this exception. Understood, students? H2PtCl6, if you directly write the dissociation, you get 2H plus and PtCl6 whole -2. If you want to name with the rules of IUPAC nomenclature for complexes, you should write hydrogen hexachloroplatinate 4. But in reality, its name is hexachloroplatinic 4 acid. Why? Why? Because this is a complex acid, not a salt. Got it?
Yes, sir.
Yes, sir.
Yes, very good. Name this FeH2O taken 5 NOSO4. Browning complex, famous complex. You might have known this. You might have done the salt analysis also. In that, you will be using this Browning test as well. So try to name this compound, IUPAC name. FeH2O taken 5 NOSO4. Students generally get out here. Sir, you have said FeH2O taken 5 NOSO4. Sulfate, we know it exists in -2 state. H2 is a neutral ligand. But what is NO? Is it a neutral ligand or NO plus? That is the point you need to understand here. Dissociation happens. How the dissociation happens? FeH2O taken 5, NO whole +2 plus SO4 -2. If NO oxidation state is +1, then what happens? We have 1 iron, so 1 into X, 5 H2O. H2O is neutral, so 5 into 0. NO, 1 NO is there. If it is in +1 state, then it should have +2 as the complex ion. So X should be is equals to +1. And this is true. The oxidation state of NO is +1. That is, NO is present in the NO plus state. Write down the name now. Penta, because H2 and NO. NO is nitrocilium, H2O is aqua. First comes A, so that is why you have to name H2O first. Penta aqua. Only one NO is there. NO plus, of course, nitrocilium. Penta aqua nitrocilium. And here iron is in the complex cation, not the anion. So you have to write iron only. If it is in the anion, you should write ferrate. Penta aqua nitrocilium iron. The oxidation state of iron is 1. That is important. The oxidation state of iron is 1 because, and we have also seen the calculation of oxidation state. This oxidation state of iron 1, you can remember. If you remember this, you can easily figure out what type of ligand is present, NO or NO plus. So penta aqua nitrosilium iron 1 sulfate, this is a correct IUPAC name. And the oxidation state of iron in the brown ring complex is +1.
So,
Yes, Prachi?
regarding oxidation state of nitrosyl, how will we know that? By distributing the charge equally first.
No. We don't know that NO or NO plus is present. The people have already studied and they have figured the ligand present in the Brownian complex is the NO in the +1 stage. Okay. This will be known after characterization techniques of this complex. Characterization techniques means these are the experimental techniques like XRD, IR, UV visible, NMR. These are all high level techniques. People study the characterization properties of a complex. From that characterization techniques, they will know what type of functional groups are there, what type of metals are there, what type of ligands are there, and from that only they will give the information. So in the brown ring complex, NO is in the +1 state, that was the ligand, but they don't need to mention that preferentially. They can simply mention NO. Are you getting this or not?
Yes, sir.
Okay, NO is in the +1 state, that we have to know, because in the brown ring complex, nitrosilium ion is there. If you know this, then only we can find out the oxidation state of iron. Or if you remember the oxidation state of iron, then you can reversely figure out what is the oxidation state of NO. You will get +1. That means you can also say nitrosilium is present. Okay, this NO plus is there, that has been given as experimentally, that in the brown ring complex, these are the ligands present. This is the metal ion, and this is how the dissociation happens. Got it now?
Yes, sir.
Yes. CuH2O taken for SO4.H2O. It is also called as blue vitriol. What is the name of this? CuH2O taken for SO4.H2O. Sorry. CuH2O taken for SO4.H2O. If you look at the name, obviously it's dissociation you have to write down. So only logic here is .H2O is there. So after using your all IUPAC rules, you have to keep monohydrate. Okay. So it dissociates to give what? CuH2O taken 4 whole +2 plus SO4 -2. First you have to name the cation. So cation is the complex ion. In the complex ion, while naming, you have to name ligands first. So only one type of ligand, that is water. And how many are there? 4 are there. So tetra aqua, tetra aqua, copper. Oxidation state of copper is 1 copper is there, 1 into X. 4H2O, 4 into 0, that is equals to +2. So X should be is equal to +2. X is the oxidation state of copper. So tetra aqua copper 2 sulfate dot monohydrate, because it is hydrated. If it is .2H2O dot dihydrate. In case in all the 4 options there is no hydrate mentioned, then you can stick with your option like tetra aqua copper 2 sulfate. Understand what I am saying? If the question has been given as what is the IUPAC name of this particular compound, and options are given to you like tetra aqua copper 2 sulfate without monohydrate in any of the option, then you have to choose this one. In case one option is tetra aqua copper 2 sulfate, other option is tetra aqua copper 2 sulfate dot monohydrate, then you have to choose this one. Got it? Try to name this. K2PtCl6. This is a simple complex. It dissociates to give 2K plus PtCl6 whole -2. So oxidation state of platinum, X, let us say 1 platinum, 1 into X, 6 chlorines, 6 into -1, that should be is equal to -2. So X should be is equal to +4. First you have to name the cation, potassium, then anion. Potassium hexachloroplatinate 4. Yes or no? Potassium hexachloroplatinate 4. These are the different examples which gives you idea regarding the oxidation, regarding the IUPAC names of exceptional compounds as well. Is that clear, students?
Yes, sir.
Yes, sir. Yes.
Yes, very good. We try to name the next compounds. IUPAC nomenclature for bridging complexes. Like whenever you have a bridge, how to figure out the IUPAC name? For nomenclature of bridging ligands, we use the prefix like mu, because if you look at this OH is actually bridged between this metal copper and this other metal cobalt. Yes or no? Between this cobalt and the other cobalt, you have OH and NH2, which are acting as a bridged ligands. Bridge means connecting the two metals. So these are bridged ligands, OH and NH2. NH3, they are not bridged ligands. These ammonia are not the bridge ligands. If it dissociates, what type of ions it gives? NH3 taken 4, CO, OH, NH2, CO, NH3 taken 4, whole plus 2 or plus 4? Sulfates, how many are there?
+4.
Plus 4, right? Because 2SO4, 2 minus is obtaining. So if you look at this complex cation, here you have plus 4. And what are the ligands present in this complex cation? Ammonia. Ammonia is a neutral ligand. OH, what is the charge of OH? OH is -1 charge. NH2 is -1. So if you think of oxidation state of cobalt is X, we have two cobalts. So 2 into X plus 1 OH minus 1 into -1, 1 NH2, 1 into NH2 minus OH minus NH2 minus. These are the ligands, right? So 1 NH2 minus 1 into -1, that is equals to total charge plus 4. Therefore, 2x is equals to how much, students? 4 plus 2, that is 6, or x is equal to 3. That means the average oxidation state of cobalt in this particular bridged complex, that is 3. Now we have to name the ligand. Now we have to name the complex. How? For naming the ligands, especially the bridged ligands, we have to use the prefix mu. What are the bridged ligands here? OH and NH2. What is the name of OH?
Hydroxo.
Hydroxo, NH2 amido. Yes or no? It's like obtained from NH3. So again you have to name. So this is hydroxo. This is amino, amido. So first you have to name the bridged ligands. While naming the bridged ligands, again you have to follow the alphabetical order. H and A, which should come first? Amido. So mu amido, mu hydroxo. While naming the complexes or bridged complexes, first you have to mention the bridged ligands. The bridged ligand should be named according to alphabetical order. So mu amido, mu hydroxo. After this, you have how many ammonia? NH3 taken 4, NH3 taken 4. So 4 and 4, 8. So octa amine, AMMINE, octa amine, that is true. How many cobalt are there? 2 cobalt. So dicobalt. Cobalt oxidation state is 3. Just now we have calculated 3. So this will complete your naming of complex ion, complex cation, and then sulfate. I'll repeat again, listen carefully. First you have to, whenever you are naming the bridged complex, first you have to name the bridged ligands. And naming of bridged ligands has to be done according to alphabetical order. We have hydroxo and amido, so A comes first. So mu amido, then mu hydroxo. Then how many amines are there? 8 amines. So octa-amine. 2 cobalts are there, dicobalt. Oxidation state of cobalt is 3. And then you have sulfate. Mu amido, mu hydroxo, octa-amine, dicobalt 3 sulfate. That is the correct IUPAC name of this bridged complex. Clear or not?
Yes, sir.
Yes, very good. And we can also represent this in the other fashion, like we are repeating this, right? NH3 taken for CO, NH3 taken for CO. We can also use bis tetraamine cobalt 3. Like this also you can mention. Okay. We'll look at the same thing in the next example. You try to name the students. NH3 taken for CO, OH, OH, CO, NH3 taken for Cl4. First, you have to know how the dissociation happens. The dissociation occurs like this: NH3 taken for CO, OH, OH, CO, NH3 taken for. This whole complex ion will be having +4 charge because we are having 4 chloride ions. 4 chloride ions. Now name it. NH3 is neutral ligand. So cobalt, 2 cobalts are there. So 2 into X. 2 OH minus. So 2 into -1 is equals to -4. So X should be is equals to 3. 2X is equal to +4, right? 2X is equal to 4 plus 2, that is 6. X is equal to 3. So oxidation state of cobalt is 3. Now again you have to name the complex cation first. So in the naming the complex cation, since it is a bridged complex, you have to name bridged ligands first. Both the bridged ligands are same. So can I use mu dihydroxo? Obviously, yes or no? Mu dihydroxo. After this, you have to name the next type of ligands, which are non-bridge ligands. Amines are there. How many are there? NH3 4, NH3 4. So 8 are there. So octaamine, mu dihydroxo octaamine, dicobalt. How many cobalts are there? 2 cobalts. Dicobalt. Cobalt oxidation state is 3. So dicobalt 3 chloride. Or we can also name it as mu dihydroxo bis. As I have told you earlier, instead of writing octaamine dicobalt 3, we can write mu dihydroxo. Up to here, we have named the bridge ligands. Then we have used bis. Bis means since this unit is repeated twice, I have used bis. Bis tetraamine cobalt 3 chloride. You can name in this fashion as well. Is that clear, students?
Yes, sir.
Okay, these are the different names of all the complex ions, and these are including all the exceptional cases as well. You try to solve as many questions as possible. Then you will be getting command over this concept. Let us proceed. Then we have EAN rule. Can anyone remember what is EAN rule? Effective atomic number and Sedgwick rule. Anyone remembered EAN rule?
Sir, atomic number minus charge plus 2 into the ligands.
Okay, fine. So we look at what it is. In a complex compound, if effective atomic number, EAN stands for effective atomic number. In a complex compound, if effective atomic number of central metal atom is equal to the nearest or same period inert gas configuration, inert gas atomic number, then the complex will be more stable and it is said to be following EAN rule. Effective atomic number is the total number of electrons around central metal atom in a complex compound. How this can be understood? Like we have a complex, students. Like we have complex like K4 Fe CN6. Just example, for example, have taken that complex. Here, what is the oxidation state of iron? Iron is in
Plus 2.
+2 state. Very good. If we have just iron, if we have just Fe, how many electrons should be present in Fe? If we have just iron, how many electrons should be present? 26. But iron is in which state? +2 state. So how many electrons should be present around Fe +2 now? 26 minus, right?
24.
Yeah, 26
Yeah,
minus.
26 minus.
Now, do we have Fe +2 ion, a simple ion, or Fe +2 is in the complex ion? Again, it is a complex ion. So if we have just iron, we have 26 electrons. If we have just Fe +2, we have 26 minus 2, 24 electrons. If we have FeCN6 whole minus 4. That means in this iron is in +2 stage, and Fe+2 is not a simple, it is present in the complex ion. What do you mean by that? That means Fe+2 has a coordinate bonds with the 6 cyanide ions. Here, how many electrons are there around Fe? In Fe+2 we have 26 minus 2. In Fe we have 26. Here we have Fe+2, 26 minus 2. If you have simple Fe+2, 26 minus 2, that's all. But Fe+2 is in the complex ion, so 26 minus 2 plus here the Fe+2 in this complex ion, is that getting electrons from the cyanides or not? 6 cyanides are giving electrons to the Fe+2 or not? Yes or no, Vaidehi?
Yes, sir.
So every cyanide is giving how many electrons? Every cyanide will be giving 2 electrons. We have 6 cyanides, so 6 into 2. Yes or no?
12. Yes, sir.
So this is the number of electrons around central metal atom or not? Got it now? Effective atomic number is the total number of electrons around central metal atom in a complex compound. This you can write down in the formula. What is 26? What is 26? 26 is nothing but atomic
Atomic
number.
number.
Yeah, very good. 26 is nothing but atomic number. What is 2 here? 2 is the
Oxidation.
oxidation stage. Very good. What is 6 into 2? 2 times that of coordination number. So you can use this formula. Effective atomic number is equals to atomic number of the metal atom minus oxidation state plus 2 times that of its a coordination number. This is the effective atomic number, which indicates the number of electrons present around the central metal atom in the complex. In this complex, the number of electrons present around the central metal atom, that has been given using your effective atomic number. If this effective atomic number is equal to nearest inert gas atomic number, then we say that particular complex is stable. If not, it is less stable. Okay, so this rule is mainly applicable for metal carbonyls. We can actually talk about stability of complexes. This is what they are saying. If effective atomic number is equal to the nearest inert gas atomic number, then the complex will be more stable, and it is said to be following EAN rule. And the formula to calculate EAN is atomic number of the metal ion minus oxidation state plus 2 times that of coordination number. Let us look at few examples. K4FeCN6, the same example they have given. What is for K4FeCN6? Effective atomic number is equal to atomic number of iron 26, oxidation states 2 plus 2 times that of coordination number is 6. How much it is, students? 26, 24, 24 plus 12, 36. Is 36 the atomic number of your nearest inert gas or not?
Yes, sir. Krypton.
Yes or no? Helium, neon, argon, krypton. So 2, 10, 18, 36. So you will be having the nearest inert gas configuration. So it is going to be stable. Similarly, find out effective atomic number in this particular complex. CuNH3 taken 4SO4. Dissociation write down. CuNH3 taken 4 whole plus 2 plus SO4 2 minus. Copper is in the oxidation state of X, let us say. So 1 into X, 4 ammonia. So 4 into 0, that should be equal to plus 2. So X should be equal to plus 2. So effective atomic number is equal to copper. Atomic number how much? 29 minus oxidation state is 2 plus 2 times that of coordination number. How much it is? 4 ammonia are there. All are monodentate ligands. So 2 into 4. 27 plus 8. Yes, students, 35. So 35 is not equal to 36. 36 is nearest inert gas atomic number.
Sir, is it +2 or -2?
X is plus 2. Okay. But we have to subtract that oxidation number, right? Formula, what is the formula? Effective atomic number is equals to atomic number Z minus oxidation state plus 2 times that of coordination number. So Z is 29. What is the oxidation state of copper? It is plus 2. So 29 minus 2, minus of plus 2, plus 2 times that of coordination number is 4. Got it or not?
Sir, sir,
Yes, Suman.
over there it is written, na?
Yes, Suman.
Sir, over there it is written, na, it is applicable for metal carbonyls. Sir, why it is so?
No, not only applicable for metal carbonyls. Metal carbonyl stability generally explained by this rule. That's it. We can apply to this to any rule, any complex.
Okay, sir.
But ultimately, it is not the final rule, Suman. You cannot say effective atomic number is equal to inert gas. So that is the most stable. There are many rules for explaining stability of complexes. Out of all those rules, one comes the chelation. Yes or no? There are many rules to explain the stability of complexes. Those rules are chelation, oxidation state of metal ions, oxidation state of metal ions. So wherever the metal ion oxidation state is differing, there the metal ligand bonds are going to be differing. And also, if you have a strong field ligand, then they will form the complexes easily. So there are different rules, like stability constants also comes, capital case. So out of all those rules, this EAN is one of the rules which explains stability. Okay?
Okay.
Look at these, students. Look at this. Any doubt if you have? Cu initially taken for SO4. Just now we have figured out. Metal oxidation state is +2. Atomic number of the metal is 29. Coordination number is 4. Effective atomic number is 29 minus 2 plus 4 into 2. That is equal to 35. Okay? We are applying not only for carbonyls. For any compound, we can apply the EAN rule. But mostly, people talk for metal carbonyls. CO initially taken 6Cl3. Cobalt is in which oxidation state? Cobalt. +3 state. Atomic number of cobalt 27. Coordination number 6 ammonia 6. So now apply a formula 27 minus 3 plus 6 into 2, that is equal to 36. Yes or no? K2Hg(I4). Metal oxidation state +2. Atomic number of the metal is 80. Coordination number is 4 because 4 iodines are there. So 80 minus 2 plus 4 into 2, that is equal to 86. Ag NH3 taken 2 whole Cl. Silver is in which oxidation state? 1 silver 1 into X plus 2 ammonia 2 into 0. Yes or no? That should be is equal to +1. So X should be is equals to +1. Oxidation state of silver is +1. Atomic number of the metal is 47. Coordination number is 2. So 47 minus 1 plus 2 into 2. Out of all these, how many are satisfying? Like if I give numbering 1, 2, 3, 4. Out of the 4 complexes, how many are satisfying EAN rule? (36). After 36, so first you have 18. Yes or no? 10 neon, or above that you have helium. Helium, neon, argon, krypton. After krypton, what do you have, students? How much is the atomic number of xenon?
54.
54.
54. After 54, how much you should add? You are adding 18 here. You are adding 18 more here. How much you should add after 54?
32.
32. How much it is results in? 86. So that is your radon. Yes or no? So 36, 86, 36, 86, they are matching with the nearest inert gas. So K2Hg(I4), CO initially taken 6Cl3, they are forming EAN rule. Following EAN rule. What about Cu is taken for SO4? 35, not following. 50, not following. 54 should be there. So like that, you can calculate the effective atomic numbers. If the effective atomic number is only the difference of 4 complexes, then you should go with the stability based on effective atomic number. Right? Try to answer this. Which of the following does not follow EN rule? Simple question.
The following does not follow EN rule.
Yeah, which one? Kanishka? Which option?
Fourth option.
Option 4.
Okay. Option is going to be here. You have chromium, iron, nickel. All these are having atomic numbers of even numbers, right? And you have, like, you can use the logic also, because cobalt is there, carbon monoxide is there, carbonyls are there especially. So 4 carbonyls, so 4 into 2 you will do, 5 carbonyls, 5 into 2 you will do, 6 carbonyls, 6 into 2 you will do. That means you are having even number here. In every complex you have oxidation state is 0. So atomic number should also be even, then only you will get even 36. So manganese is 25, which is odd number. So there you cannot have. So that is your right option. Find out the value of X if the following complexes form the or follow the EN rule. Do it for FeCOX. 26 minus 0 plus 2 into X, that should be is equals to 36. So 2x is equals to 36 minus 26, 10. So 2x is equals to 10 means X is equal to 5. Will you solve the other two or not? In the same way. If you want, you can solve. Chromium 24, oxidation state is 0, neutral complex, plus 2 into X, that should be is equal to 36. So 2x is equal to 12, X is equal to 6. Solve it. So like that, if the complex is following effective atomic number rule, then we can actually calculate the number of ligands present and also determine the coordination number, right? Then comes the theory, students. Up to now, whatever you have studied, like from the starting to till now, whatever the concepts we have studied, they are just like basic concepts. Our coordination chemistry starts when you try to explain the bonding. What type of bonds are there in the complex? How these bonds are formed? The complex has what type of structure? Yes or no? Up to now, whatever the things we have studied, just like basic terminologies, the nomenclature, the EAN rules, the carbon monoxide back bonding, synergic bondings. Yes or no? All these ligand classification, metals classification, what are double salts, what are complexes. But now we need to understand, yes, we have known that there are complexes. We know how to define the complexes, how to give the names of the complexes, how to how to understand their terminology. But you have to explain how the bonding has been happening in the complexes. To explain bonding in complexes, there are 3 theories, especially in our 12th standards. Of course, these 3 theories have some drawbacks also. We still have advanced theories which are not in our course of syllabus. But we have to study 3 theories for minimum. What are those 3 theories? Werner's theory, valence bond theory, and crystal field theory. After the crystal field theory, we have ligand field theory. After that, we also have charge transfer phenomenons. Yes or no? Those are not in our syllabus. And we also have molecular orbital theory also. The molecular orbital theory we study only in chemical bonding, but not for the complex compounds. So we'll study what is there in our syllabus and what is in what different types of ways the questions can be asked. So Werner's theory, it was a very first theory which tries to give some idea regarding the complex compounds. Werner's theory is the very first theory which tries to give some idea regarding the complex compounds. right? So in a complex compound, every central metal ion has two types of valencies. What are the two types of valencies? According to Oneness theory, in a complex compound, every central metal ion has two types of valencies: primary valency and secondary valency. So what are these types of valencies? And these types of valency will give what type of idea? We'll be looking now. So according to Warner, whatever the complex you have been given, it has two types of valencies: primary valency and secondary valency. What is primary valency? It is the oxidation number of central metal atom or central metal ion. What is the oxidation state? That is nothing but your primary valency. Secondary valency is it is a coordination number of central metal ion. Coordination number of central metal ion. Primary valency, it is satisfied by negatively charged species. Primary valency, because oxidation states or oxidation number you are getting, that is metal will have some positive charge, that has to be satisfied by negatively charged species. Whereas secondary valency, in the coordination number, what do we have, students? We can have neutral ligands, we can have positively charged ligands, we can have negatively charged ligands. Every ligand in the coordination number, like I have a complex like K4FeCN6. In this complex, we have 6 cyanides. All of them are negatively charged ligands. I can also have complex like K4 FeH2O taken 5 Cl. Like arbitrary complex I am writing. Yes or no? So the complex, whatever you are going to write, in the coordination sphere, you can have ligands. The ligands can be positively charged, negatively charged, or neutral. That means secondary valency is actually giving an idea regarding the coordination number, right? So that means it is satisfied by negative, positive, and neutral. All of them can satisfy the secondary valency. Primary valency, it has to satisfy the oxidation state of the central metal atom. That means it is giving the oxidation number of the central metal ion. So it has to be satisfied only by negatively charged species. These are like ionizable. The primary valencies are ionizable. That means they can be leading to counter ions. Secondary valencies, that means in the complex or coordination entity, we do not have ligands which can be ionizable. And we have primary valencies which are said to be non-directional. Why? Whereas secondary valencies are directional. Primary valency like K4FeCN6, if you take the 4 K plus ions, the K plus ion and FeCN6 minus 4 ion, they will have some electrostatic force of attractions. That's it. The electrostatic force of attraction can be from any side. But if you look at a secondary valency, the ligand is going to form a bond with the metal. So from the ligand, the electrons are donated to the metal. So it is directional. The secondary valencies are directional. The primary valencies, they are non-directional, just electrostatic force of attractions. Just electrostatic force of attractions. That is why they are denoted by dashed lines. Yes or no? Why they are denoted by dashed lines? Because the electrostatic force of attraction, like you have a positive charge ion here, the negative charge can be somewhere here. We have electrostatic force of attraction somewhere here. So anywhere, it can be the positive and negative charges can be anywhere. They have some electrostatic force of attraction. That's what you have studied in electrostatics. So they are denoted by dashed lines. There is no overlapping here. Whereas if you look at secondary valencies, they have to be, there is a bond formation. So they have to be denoted by solid lines. And because of electrostatic force of attractions, can we predict the geometry? No. So primary valency cannot be predicting the geometry of the complex. And because of all the bonds formed, like you can predict octahedral or tetrahedral complexes are formed. So secondary valencies define the geometry of the complex. Are the differences clear, students?
Yes, sir.
Yes, sir.
Yes or no? All of you should respond.
Yes, sir.
Yes, sir.
Yes, very good. So simple logic, primary valency explains about oxidation number of the central metal ion. Secondary valency talks about coordination number. Primary valency is satisfied by negatively charged ions. Secondary valency by negatively charged as well as neutral. Primary valency is ionizable. Secondary valency non-ionizable. Primary valency non-directional. Secondary valency is directional. Primary valency cannot predict the geometry and is denoted by dashed lines. Secondary valency defines the geometry and denoted by solid lines. Right?
Yes, sir. Yes, sir.
Yes. Yeah, dotted line indicates primary valency. Dotted line indicates primary valency. Solid line indicates secondary valency. When you have both dotted lines and solid lines, that indicates primary and secondary valency both. What do you mean by that? That means some species can behave as both primary and secondary valencies. Some species can behave as both primary and secondary valencies. We look at what are that species. So Werner's representation, there is a complex of molecular formula COCl3.6NH3. How he has represented this complex is, he said that all the 6 NH3 will be acting as ligands, CONH3 taken 6 whole Cl3. Whenever a complex has been given to you with this formula, he has written like CONH3 taken 6 Cl3. Now you will be having a doubt. Any student, they may ask like, sir, how we can say that all the 6 ammonia are actually involving in the coordinate bonds and all the 3 chlorines are acting as counter ions? Why can't you take the probability and take out of the 6 ammonia, let us say 4 ammonia are actually involving in coordinate bonds and the remaining 2 ammonia, they can act as a counter ions or they can be outside. Why can't you take that possibility? That is true, right? Yes or no? But what he studied is Werner's representation. Whatever the representation he has given, it is not arbitrarily given. It has been given by studying the conductivity experiments. Anyone know conductivity experiments? What is conductivity? You have studied in electrochemistry. Like if the CONH3 taken 6 Cl3, if that dissociate, what type of ions you are getting? CONH3 taken 6 whole plus 3 Cl minus. So how many types of ions are getting, students? How many ions are there? The number of ions obtained by the dissociation of this complex is how many?
4
One
ions.
complex. Yeah, 1 complex ion and 3 chloride ions. So 4 ions you are getting. Does the conductivity depend upon the number of ions or not? Greater the number of ions, greater will be the conductivity. Yes or no? Greater the number of ions, greater will be the conductivity. So based on conductivity experiments, he has given this formula. By combining, by studying the conductivity of different complex ions, he has given the formula. So CONH taken 6 Cl3. So if you understand this, it is dissociating into CONH taken 6 whole plus 3 Cl minus. In this complex, which are ligands, students? Ammonia are ligands or not? So which are actually secondary valencies? Secondary valencies are what?
NH3.
NH3. Primary valencies? Primary valencies?
Cl3.
Cl minus. Chloride ions are actually the negatively charged ions which are supporting your primary valency. Ammonia, they are actually ligands which are bonded to cobalt. They are acting as secondary valencies. So we have cobalt. It is bonded with 6 ammonia. So 6 solid lines. It has electrostatic force of attraction with 3 chloride ions. So that is represented by dashed lines. So this is your complex CONH3 taken 6 Cl3. Is that clear? This is how Werner has represented the complex. And whenever you have 6 ligands, it will occupy a shape of octahedral. Clear or not?
Yes, sir.
Werner theory has a lot of drawbacks. Like arbitrarily, they are saying this is octahedral complex. NH3 is forming a bond with cobalt. But did they say any information regarding the type of bond form? How the bonding is happening? What is the hybridization? All these things were never explained by Werner because he don't know at that time. Werner's theory was the first theory which tries to explain about the complex compounds. He has given his first effort Later on, there are a lot of drawbacks in Warner's theory. He could not explain color. He could not explain the hybridizations. He could not explain the type of bond form and why only such type of bonds formed. Only he has just said there are two types of valencies. Based on that, he has categorized the molecules. So these three chlorides are primary valency. So oxidation number should be equal to 3. 6 ammonia, that is your secondary valency. Coordination number is equal to 6. If you remove 1NH3 from COCl3.6NH3, you are getting COCl3.5NH3. How this complex exists, students? COCl3.5NH3. Cobalt is in +3 state or not? COCl3 means. COCl3.5NH3 means 3 chlorides were actually present in this COCl3. So cobalt should be in +3 state. What do you mean by that? That means it is forming a complex of coordination number 6. But out of that 6 coordination number, there are only 5 ligands, 5 ammonia present. What about the 6th ligand? That should be chlorine. So it can be represented as CONH3 taken 5, Cl and Cl2. Right or not? CONH3 taken 5, Cl and Cl2. This is how you have to mention this formula. So you know 5 ammonia act as secondary valency. These 2 chlorines will act as primary valency. What about this chlorine here? What about this chlorine which is having negative charge and which is present inside? It is a primary valency or secondary valency?
Secondary valency.
Secondary.
Sure? Or is it second? With using this chlorine only, we can say the oxidation number of cobalt is 3, or without this chlorine also we can say. Like how to calculate the oxidation state of cobalt? We can say dissociation happened. CONH3 taken 5, Cl whole +2 Cl minus. 1 cobalt is there, 1 into X, 5 ammonia, 5 into 0, plus 1 chlorine is there, 1 into -1, that should be is equal to +2. From here you are saying +3 is the oxidation state of cobalt. You are using the negative charge of chlorine or not to explain the oxidation state, to explain the oxidation state of metal ion. You are using the negative charge of Cl or not? Yes or no?
Yes, sir.
Yes, sir.
So this chlorine is also responsible for oxidation state or not? This chlorine, these two are obviously responsible. This chlorine is responsible or not? It is also responsible. So can I call this not as a primary valency? No, it is also used to determine the oxidation state of cobalt. So this chlorine should be a primary valency also. And it should also be a secondary valency because it is bonded to cobalt. It is in the coordination sphere. So this chlorine will act as both primary valency and secondary valency. Got it? This is your CONH3 taken 6, Cl3. Now we are removing one NH3. Yes or no? One NH3 removed. So you have one Cl minus which has both primary valency nature as well as secondary valency. That means one chloride ion shows dual nature. This chlorine is also considered as a primary valency. Why? Because using the -1 charge of that chlorine only, we can say oxidation state of cobalt is +3. If you do not treat this chlorine, then oxidation state of cobalt should be +2 only, which is wrong. We are taking the chlorine which was present in the coordination sphere and then determining the oxidation state as +3. That means this chlorine is also acting as primary valency. Also, this chlorine is bonded to cobalt because it is in the coordination sphere. So it is acting as secondary valency. So this chlorine acts as both primary valency and secondary valency. So it shows dual nature. Got it, students? Clear or not?
Yes, sir.
Yes, very good. So let us take another complex, COCl3.4NH3. Okay, primary valency is equals to oxidation number, that is equal to 3. Secondary valency is equal to coordination number, that is equal to 6. So let us take other complex. Like I have given a complex to you like this, COCl3.4NH3. How to explain this complex, students? How to write this formula? CONH3 taken 4, Cl2 whole bracket Cl. Yes or no? So what about this chlorine? Primary valency or secondary valency?
Primary.
Primary. What about this 4 ammonia?
Secondary.
Secondary.
Secondary. What about these 2 chlorines?
Secondary.
Second.
Primary. Dual nature.
Right? Primary and secondary. Right? That is how you need to understand what type of valencies are there and what is their nature. Now, possible formula of COCl3.6NH3 .6H2O, not 6NH3. Possible
First
formula. Yeah, COCl3.6H2O is COH2O taken 6 Cl3. Yes or no? If this compound dissociates, how many moles of AgCl will be obtained? That is the question I'm asking you.
3 moles.
3.
Yes or no? Because this complex, if it dissociates, it is giving 3 chloride ions. So 3 chloride ions can react with 3 Ag plus ions to form 3 moles of AgCl. If you mix this complex with Ag and O3, number of moles of AgCl obtained is 3. 3 moles. Number of ions obtained, total number of ions obtained after the dissociation of that complex?
4.
3 chloride ions. Yeah, 3 chloride ions and 1 complex ion. So 4. Yes or no? That is how we can have different questions. I'll give some more examples. Just to confirm, is everything clear so far or not?
Yes, sir.
Yes, sir.
Yes, very good, all of you. Now you have to do this, students. Okay, I'll do for first question. PTCl4.6H2O. What is a complex compound? How to write the complex compound? PTCl4.6H2O. I have to write all 6 H2O inside and 4 chlorines outside. PTH2O taken 6 Cl4. How many Cl minus act as primary valency and secondary valency both?
0.
0. Very good. Total number of ions in aqueous solution?
5.
5. Very good.
5.
Total number of moles of AgCl when AgNO3 is used?
4.
4. Very good. Percentage of ionizable chlorine?
100.
100%. Right? Very simple. The same discussion is going to happen. Here you have PTH2O taken 5 Cl and Cl3. PTH2O taken 5 Cl and Cl3. So you have how many chlorines acting as both primary valency and secondary valency?
1.
1. Total number of ions?
4.
4. Very good. Total number of moles of AgCl obtained?
3.
Because 3 chlorines are there. Percentage of ionizable chlorine?
75.
75%.
Very good. Like that, we can write down the PTCl4.4H2O, PTCl4.3H2O. So PTH2O taken 4 Cl2 whole Cl2. So 2 chlorines act as both primary and secondary valency. 3 ions are there in the solution. 2 moles of AgCl obtained. 50% is the percentage of ionizable chlorine. You may ask a question, sir, how you are saying that only all the 6 H2O are acting as ligands? I have told you that he has studied the structures of complexes based on conductivity experiments. Using conductivity experiments, he has given this data. Right, students, this is all about your Werner's complexes and Werner's theory. So he has not given any information regarding the hybridization, no information regarding color, no information regarding magnetic nature, no information regarding the type of many things, what type of bond is formed, how the bonds are formed. Just says primary valencies and secondary valencies. And when a complex is added to excess of AgNO3, how many moles of AgCl obtained? Based on that, he said how many chloride ions are coordinated. Like that, some simple or basic concepts or basic theories of complexes have been explained. Yes or no? So what you can do instead? What you can do instead is, I have taken this complex, I don't know its formula. I have taken the complex PTCl4.6H2O. One thing is he has used the conductivity experiment. The other way what he has done is, he has taken excess AgNO3. When he take excess AgNO3, from this complex you are going to get AgCl. From this complex you will get some chloride ions. That Cl minus will be reacting with Ag plus to form AgCl. AgCl is a precipitate. Calculate its weights. Okay. Calculated the quantity of AgCl. From the quantity of AgCl, can I calculate the number of moles of AgCl or not? Yes or no? Therefore,
Yes, sir.
number of moles of AgCl can be figured out, can be calculated. Because he has just added AgNO3 to that complex. He produced AgCl, removed all the water, taken the precipitate out, calculated with the apparatus, whatever available at that time. So calculate the quantity of AgCl. Number of moles of AgCl can be calculated. Number of moles is equals to weight by molecular weight. Calculate the number of moles of AgCl. Now write the dissociation. AgCl gives Ag plus plus Cl minus. Can I say one molecule of AgCl gives one molecule of AgCl gives one Cl minus ion, because it is giving only one Cl minus ion. So if you take one molecule of AgCl, it is giving one Cl minus ion. If you take Avogadro number of molecules, how many Cl minus ions it gives?
Avogadro's number.
Avogadro number. So Na molecules gives NaCl minus. So Avogadro number of molecules, can I call Avogadro number of molecules as 1 mole? So 1 mole gives 1 mole of AgCl gives 1 mole of Cl minus. We have calculated number of moles of AgCl, and we know 1 mole of AgCl is giving 1 mole of Cl minus. That means from the number of moles of AgCl, can I say number of moles of chloride obtained? Yes or no?
Yes.
From the number of moles of AgCl, you can write down this. From the number of moles of AgCl, we can calculate the number of moles of Cl minus. We can calculate the number of moles of Cl minus. And we are actually taking the complex. Yes or no? Whatever the complex I am taking, I'll measure that. How much complex I have taken. Its molecular weight I'll calculate. So complex weight and molecular weight both are known. So number of moles of complex I known. So now from the complex, we can calculate its number of moles. That means how much quantity of complex you have taken. From that you can calculate the number of moles of complex, and from that you can also say how many number of moles of Cl minus obtained. So can I relate these two, students? If I take 1 mole of complex and if I am getting 2 moles of chloride ions, can I say 2 Cl minus or 2 chlorines are outside of the coordination? Yes or no? If I am taking just 1 mole of complex and if I am getting 2 moles of chlorides, what do you mean by that? That means this is a scenario. 2 chlorines are outside. If I am taking 1 mole of complex and if I am getting 4 moles of Cl minus, then this was a scenario. Are you understanding this or not?
Yes, sir.
From the number of moles of AgCl obtained, we can figure out the formula of the complex, like how many chlorines are inside the complex, inside the coordination sphere, how many are acting as counter ions. So one thing based on conductivity experiments, we can say this is the formula. One thing based on the number of moles of AgCl also, we can predict number of chlorides outside the coordination sphere. So like this, we can study the Werner's complexes. Right, let us proceed to the next theory, students. Next theory is valence bond theory. This theory was mainly developed by Linus Pauling. The main features of this theory are: metal ion, when it forms a complex compound, undergoes formation of coordinate bond. This was the theory which I have been talking earlier. Like metal ion, we have written metal ion and we have a ligand. The ligands actually donate the electron pairs into ligands donate electron pair into empty d orbitals of metal. What do you mean by that? That means metal ion, when it is a form, metal ion, when it forms a complex compound, undergoes formation of coordinate bond. During this coordinate bond formation, metal ion acts as electron pair acceptor. For this, the metal ion has to provide vacant orbitals according to its coordination number. Simple thing, nothing much. we have a metal ion. The metal ion is not free, it is in the complex ion. In the complex ion, whatever the metal we have, that will have some empty d orbitals or empty orbitals in the outermost shells. Because of the presence of empty orbitals, it will accept electrons from the ligand. Ligand is donating the electrons, metal is accepting the electrons. So metal act as electron pair acceptor, ligand act as electron pair donor. This is the basic postulates of valence bond theory. Understood these points? Yes or no?
Yes, sir.
What Farhan, understood or not? Okay, fine. Like example, in the formation of FeCl6 3 minus, in the formation of FeCl6 3 minus, Fe plus 3, write the electronic configuration. Fe, argon, Fe plus 2, if you say Fe plus 2, argon, 3d6, right? 3d6, 4s, and then you have 4p and then 4d. This is 4s, 4p, 4d, and this is your 3d. Fe plus 2 means you will be having electronic configuration of argon 4s0, 3d6. In the 3d, we have 6 electrons, 3d6. In the formation of FeCl6 3 minus, I'll ask simple questions. You have to answer one by one fastly. How many ligands are there?
6.
6 ligands. Each ligand provide how many electrons?
2.
2. So 6 ligands provide how many electrons?
12.
12.
Very good. So every atomic orbital can have a maximum how many electrons?
2.
2. 12 electrons we have. We have to give the 12 electrons to how many number of ligands? Maximum number of vacant orbitals required for giving 12 electrons. Maximum number of vacant orbitals required to have 12 electrons. 6, no? Yes or no? FeCl6 3 minus, 6 ligands are there, 6 into 2, 12 electrons are obtained. So one orbital can have a maximum of only 2 electrons. So 6 orbitals we have to require. So 6 orbitals from where we have to require? From the metal ion. Yes or no? Write down orbitals of Fe plus 3. So here we have mentioned clearly. Fe plus 3 they are talking, right? We have written for Fe plus 2. Fe plus 3 means 3d5 will have, not 3d6. So 3d5, that means according to your Hund's rule, you will be giving 1 electron to each d orbital. And after 3d you have 4s, 4p, 4d, which are empty. Now we have Cl minus. The 4s, 3, 4p and 2, 4d, they are vacant. So these are the vacant orbitals. Because of the presence of these vacant orbitals, what it can do? Cl minus, Cl minus, Cl minus, Cl minus, Cl minus, 6 Cl minus. 6 Cl minus, they can donate electrons into these 6 vacant orbitals or not. So what type of hybridization we are having, students? sp3d2. What is the hybridization? sp3d2. Yes, right? Got it or not?
Yes, sir.
Yes.
Now we'll ask a simple question. So on what basis you are going to say that Cl will occupy electrons only from 4s, 4p and 4d? Why not Cl pair up the electrons in 3d and occupy the empty orbitals in 3d? That has to be decided based on strong field ligands and weak field ligands. Cl minus is a strong field ligand or weak field ligand?
Weak.
Okay, we are going to decide which ligands are strong field ligands or strong ligands, which ligands are weak field ligands. From that only we can say whether the pairing in the inner d orbitals will happen or will not happen, right? Next, you try to answer the students. CuF42 minus Cu plus 2 ion provide how many vacant orbitals? 4 vacant orbitals. Why? Argument starts like this. Listen carefully. We have 4 ligands. Each ligand gives 2 electrons. 4 ligands will give how many electrons? 4 into 2, 8 electrons. 8 electrons are given by ligands. So in the metal, you should have vacant orbitals. How many? Every atomic orbital will occupy 2 electrons. So to occupy 8 electrons, how many atomic orbitals are required? 4.
4.
Yes or no? Very good. So Cu plus 2 has to provide 4 vacant orbitals. What is the electronic configuration of Cu plus 2? Orbitals of Cu plus 2? You have 3d, 4s, 4p. Cu plus 2 means copper means argon 4s1, 3d10. Copper plus 2 means from the 4s 1 electron is lost. From the 3d you have removed 1 more electron. So you have argon 3d9. Argon 3d9. After 3d you have again 4s 4p which are vacant. And again F minus fluoride is also a weak field ligand. It cannot pair up, and there is no possibility of pairing also, because only 1 electron is present in 3d which cannot pair up with any other species. So you have 4s and 4p. This 4s and 4p, they are your vacant orbitals. So what is the hybridization you can expect here? sp3 hybridization, right? So whatever I have told you up to now, like FeCl6 3 minus, CuF42 minus, in these complexes we have just looked at what are the available vacant orbitals. These vacant orbitals undergo hybridization before bond formation with ligands. That is the point. Like what I have told you. So these are the vacant orbitals, right? We cannot directly say F minus gives electrons to S. What we have to say instead is the 4s and 3,4p, they will intermix to form 4 sp3 hybrid orbitals. Once you get the 4 sp3 hybrid orbital, the ligand is donating electrons into sp3 hybrid orbital, not into the atomic orbital of the metal. The ligands are donating their electrons to the hybrid orbitals, not to the empty atomic orbitals. These ligands, these vacant orbitals undergo hybridization before bond formation with ligands. So you can see how the hybrid orbitals are formed. Look at the animation or not? I'll play it again. Listen. Observe carefully. See. So we have 4s, 4p, 4px, 4py, 4pz, 3d x square minus y square, 3d z square. All of them, they are going to be intermixing. If they intermix, they will form what? They will form 6 sp3 d2 hybrid orbitals in case of FeCl6 3 minus. Yeah, the vacant hybrid orbitals. Now we have hybrid orbitals, no? These vacant hybrid orbitals of metal ion gets overlaps with the orbitals of ligands containing lone pair of electrons. Earlier we have said in the ligand we have lone pair of electrons, in the ligand we have lone pair of electrons. Like let us take a ligand like ammonia. Where is the lone pair of electrons of ammonia present? In ammonia, where is the lone pair of electrons present?
On
nitrogen.
On nitrogen, but where on nitrogen? That's what I'm asking. Nitrogen, okay, but where? In the nucleus of nitrogen? If you look at ammonia, what is the hybridization of ammonia, students?
sp2.
Write down the electronic configuration.
S
Write down the electronic configuration of nitrogen. This is a simple molecule, right? 1s2, 2s2, 2px1, 2py1, 2pz1. That is the electronic configuration of nitrogen. There is no excitation possible. So if you try to look at the electronic configuration of nitrogen, you have 2s, 2px, 2py, 2pz, which are having electrons. Now the 2s, 2px, 2py, 2pz, they have similar energy. So 2s, 2px, 2py, 2pz, 2py plus 2pz will overlap or will intermix, not overlap, will intermix to form how many hybrid orbitals?
4.
4. What type of hybrids?
sp3.
Right. So 2s, 2px, 2py, 2pz will intermix to form 4 sp3 hybrid orbitals. Out of these 4 hybrid orbitals, once the hybrid orbitals are formed, they will arrange the minimum repulsion state. Whenever you have 4 sp3 hybrid orbitals, what is the minimum repulsion state? Whenever you have 4 electron pairs, what is the minimum repulsion state? Tetrahedral. Whenever you have only 2 hybrid orbitals, they will arrange in the linear fashion. 3 are there means they will arrange in the trigonal planar fashion. 4 means tetrahedral fashion. But what are now arranging in the tetrahedral fashion? The sp3 hybrid orbitals, not the s orbital, not the p orbital. The shape of sp3 hybrid orbital will be like this. Why I have drawn the shape of sp3 hybrid orbital in this manner? Because in the sp3 hybrid orbital, what is the percentage of s character?
25%.
What is the percentage of p character? 75%.
75%.
So sp3 hybrid orbital looks more like p orbital or s orbital?
P orbital.
P orbital. So that's why we have drawn the shape of sp3 hybrid orbital in this manner. Once these sp3 hybrid orbitals are formed and they are arranged, now look at the number of electrons. In the atomic orbitals, 2s, 2px, 2py, 2pz, in the 2s atomic orbital, how many electrons are there? 2 electrons are already there. In the 2px, we have 1 electron. In the 2py, we have 1 electron. In the 2pz, we have 1 electron. So in total, we have 5 electrons. So these 5 electrons should be again matching with the number of electrons in the sp3 hybrid orbitals or not? For sure, we cannot remove the electron. We cannot add an electron. We have 4 sp3 hybrid orbital. We say that out of these 4 sp3 hybrid orbital, 3 sp3 hybrid orbital will have 1 electron each, and the other sp3 hybrid orbital will have 2 electrons each. So 5 electrons are there. Same with their atomic orbitals. Now the hybrid orbitals formation has been seen by intermixing of atomic orbitals. The arrangement of hybrid orbitals has been seen, and electrons in the hybrid orbitals have also been seen. Now finally what happens? The overlapping with the atomic orbitals of other atom. Hydrogen is other atom. 1s1 is the atomic orbital of hydrogen. So 1s atomic orbital of hydrogen overlaps with 1s atomic orbital of hydrogen overlaps with sp3 hybrid orbital of nitrogen to form your NH bond. What is your NH bond? In ammonia, the NH bond is formed by overlapping of 1s atomic orbital of nitrogen with the sp3 hybrid orbital, 1s atomic orbital of hydrogen with the sp3 hybrid orbital of nitrogen. What happened to the 2 electrons present in one more sp3 hybrid orbital? This is sp3 hybrid orbital, right? These 2 electrons, can I call this as lone pair? Yes or no?
Yes.
Yes, sir.
The 2 electrons present on nitrogen, they are said to be lone pair, but where are they actually? They are in the sp3 hybrid orbital of nitrogen. On nitrogen, we have lone pair, that's fine, but where are they? They are in some hybrid orbitals or atomic orbitals. The same thing they are saying here. The vacant hybrid orbitals of metal. We have just now seen how the hybrid orbitals in the metal are formed. These vacant hybrid orbital of metal gets overlap with the orbitals of ligands. Orbitals of ligands containing lone pair of electron. That means lone pair of electrons are not present orbitally on the atom. They have to be present on respect to orbital. The orbitals of ligands containing lone pair of electrons, they will overlap with the vacant hybrid orbitals of metal. If the ligand is ammonia, which orbitals are having the lone pair of electrons on ammonia?
sp3.
sp3.
So this sp3 hybrid orbital of nitrogen is sp3 hybrid orbital of ammonia that will overlap with the hybrid orbital of metal. So let us say sp3d2 is the hybridization. The sp3d2 hybrid orbital of metal overlaps with the sp3 hybrid orbital of ammonia. In case if ammonia is forming a metal, if ammonia is forming a bond with the metal, then we can say sp3d2 hybrid orbital of metal overlaps with the sp3 hybrid orbital of ammonia. That's what they say. The vacant orbitals of metal ion get overlap with orbitals of ligand containing lone pair of electrons. Right? Is that point clear?
Yes, sir.
Yes.
Yes, very good.
Yes, sir.
Very good. See now, metal is there. In the metal, we have hybrid orbitals. From the ligand, we are giving electrons from where? Not arbitrary electrons added. We are having electrons from the ligands which are present in their respective orbitals. That is what they are saying. Look at the animation carefully. This has a lot of meaning. We have metal. In the metal, we have hybrid orbitals. These are all hybrid orbitals. A vacant hybrid orbitals. They are vacant. They do not have electrons as of now. Now they are getting electrons. From where? From the ligands. But where are the electrons and ligands are? They are in respective orbitals. Now the orbitals are going to be overlapped, which is called as your bonding. What is a covalent bond? What is a covalent bond? Covalent bond is obtained by overlapping of orbitals, either atomic orbitals or hybrid orbitals. Okay, that depends upon the type of molecule we are looking at. Understood now? So first your role is to, whenever the complex have been given to you, you find out, write down the electronic configuration of metal ion, find out the vacant orbitals, and you hybridize them. You get the hybrid orbitals. Once you get the hybrid orbitals, you have to arrange them in the minimum repulsion state. Once you have arranged them in the minimum repulsion state, you have to then make the bond formation with the lone pair of electrons from the ligands. So which lone pair of electrons from which type of ligands are going to present, that we can write down. This point is very important. If in a complex strong ligand is present, then it may cause pairing of unpaired electrons in n-1d orbitals of central metal ion, and if n-1d orbitals are involved in hybridization, then the inner orbital complex is formed. That's what we mean, right? So let us take K4 FeCN6. Cyanide is a strong field ligand. So what happened in Fe+2? We have argon 3d6. What should be 3d6? 1, 2, 3, 4, 5, 6. But what happened actually? The pairing happened. Yes or no? Because of pairing, what is available, students? Because of pairing, the inner orbitals are vacant or not? Yes or no?
Yes, sir.
If in a complex, if a strong field ligand is present, then it may cause pairing of unpaired electrons. Because of strong field ligand, the electrons in the outermost, that is the innermost n-1d orbitals, they have paired up. If they have paired up, the pairing will result in vacancy. Like two students are there in two different benches, and I make them to sit in the same bench. What happened to the other bench? That is vacant, obviously. Same here. Here we have electrons. 4 students in 4 different benches are there. Now I am just pairing them. So what happened because of pairing? I have 2 benches empty. So 2 orbitals are empty now. So the empty orbitals can involve in the hybridization. If the empty inner orbitals are involving in the hybridization, then what type of complex is formed? Inner orbital complex is formed. Inner orbital complex is going to be low spin complex or high spin complex? Inner orbital complex.
Low spin complex.
Low spin, right? Because of pairing, the spin has been decreased. So it is said to be low spin complex. Inner orbital complex is also called as a low spin complex. Next, if in a complex weak ligand is present, then there will be no pairing. If it is a weak ligand, the weak ligand cannot repel the n-1d electrons greatly. If it cannot repel, the pairing will not happen. If a pairing will not happen, the outermost vacant orbitals, they are used. That is why it is said to be outer orbital complex. It is not inner orbital complex. And outer orbital complex is also called as high spin complex because no pairing happens. The orbitals of metal ion n-1d, ns, np, and nd, right? Inner orbital complex uses these inner n-1d electrons. Outer orbital complex uses these outer Nd orbitals. Inner orbitals means inner d orbitals are used. Outer orbitals means outer d orbitals are used. Is that point clear, students? Yes or no?
Yes, sir.
Yes, sir. Yes, sir.
Yes, very good.
Yes.
And this point is very clear. If unpaired electron is present in the complex, then it will be paramagnetic. If we have an unpaired electron, it is said to be paramagnetic. If we do not have an unpaired electron, it is said to be diamagnetic. Paramagnetic are weakly attracted or weakly repelled?
Weakly attracted.
Weakly attracted.
Attracted.
Paramagnetic means weakly attracted by the external magnetic field. Diamagnetic means weakly repelled. Weakly repelled. Hybridization. SP hybridization. We look at now coordination number, hybridization, and shapes. SP hybridization means what should be the coordination number?
2.
2. SP means linear should be there. So only 2 ligands, M, L1, L2. So that is how you can have the animation. SP2 means what? SP2 means trigonal planar. And how many ligands are there? 3 ligands, L1, L2, L3. So coordination number should be how much, students? Coordination number should be 3. SP2 hybridization means trigonal planar. Trigonal planar is a possible shape. SP3 means what? SP3.
Tetrahedral.
SP3 hybridization means SP3. In the coordination number 4, we can have 2 types. SP3 tetrahedral. If you have DSP2, that is square planar. When we have DSP2, if we have DSP2, that means inner d orbitals are used. Inner d orbitals used means what? There is pairing happened. If pairing when happens, if we have a strong field ligand or not? Yes or no?
Yes.
Yes, sir.
So DSP2 is a hybridization which is possible in case of strong field ligand. And if DSP2 is the hybridization, its shape will be square planar. If SP3 is the hybridization, inner d orbitals are not used. So we have generally weak field ligands. So in that case, you have tetrahedral. Tetrahedral means if my wrist is a atom, yeah, you can have the figure here, right? 1 bond above like this means 3 bonds are like this. 3 bonds are like this. This is your tetrahedron. Understood how the shape of tetrahedron would be? Square planar. Square planar means planarity should be there, and the 4 ligands should be, if you try to connect the 4 ligands, you will get a square. Square planar. DSP2 is a hybridization. SP3D or DSP3, what is the possible hybridization, students? SP3D or DSP3, what is the possible shape?
Trigonal bipyramidal.
Trigonal bipyramidal.
Right. SP3D or DSP3, trigonal bipyramidal is going to be your geometry. Coordination number would be 5 because we have 5 hybrid orbitals. And this is going to be your minimum repulsion stage. SP3D2 or D2SP3, what is the shape? SP3D2.
Octahedral.
Octahedral, very good. Yes, SP3D2 or D2SP3, that is square bipyramidal or octahedral, both are same only. Square bipyramidal, octahedral, coordination number should be 6. You will have this type of scenario. Generally, here in our 12th standard, we will be looking at complexes of octahedral shape, tetrahedral shape, and square planar shapes. What complexes we are going to be looking at? Coordination number 4 and 6 complexes were studied detail. In the coordination number 6, SP3D2 or D2SP3, whatever the hybridization is, we have octahedral. In the coordination number 4, SP3 or DSP2, that is tetrahedral or square planar, these complexes were studied in detail. Write down this spectrochemical series. It is the experimentally given series. It is experimentally given series which explains the strength of ligand. Strength of ligand. You may ask a question, sir, why you are saying all this? We can easily say from the electronegativity or not. Less electronegative atom can easily donate. More electronegative atom can withhold the electron density. Based on electronegativity, can I comment? Not just like that, students, because we have the ions in the aqueous solution, we have the ligands in the aqueous solution, their ionic mobilities, their hydration effects, yes or no, their electronegativities. Based on all this only we get the series. It is an experimentally given series which explains the strength of ligand. Up to H2O, you have weak field ligand. Yes or no? NCS, EDTA, NH3, ethylene diamine, NO2, Cn minus CO, all these are strong field ligand. Generally, nitrogen donors and carbon donors are strong field ligands. Halide or sulfur, oxygen donors, they are weak field ligands. Note down this series. So we'll stop our discussion here. Next class, we'll continue with different other examples of your valence bond theory. Here we have seen how the valence bond theory can be understood. So we'll look at different complexes from valence bond theory, try to explain their hybridization, shape, what type of complex it is, inner orbital complex or outer orbital complex, and the exceptional cases. Right? Satyam, I have already shared my number. Okay, I'll just put it out in the comment section. If you want, you can take it out. Okay, fine, students. Thank you all, everyone, and happy Dasara to all of you.
Thank you, sir.
Thank you, sir.
Same to you, sir.
Same to you, sir.